All right, guys, welcome. Hope everybody's doing well. Welcome to another video. Today we are going to be reviewing for your 6 weeks test, okay? So before you start to freak out, don't. The 6 weeks test is just gonna cover what we've been going over recently. This includes all of the stuff about circuits and electricity, and it also includes everything that we covered about light in the electromagnetic spectrum. So I'm going to go back over this stuff with you guys. As I'm going over this review, I recommend that you write down some notes because this will be very helpful when you're actually taking your test, okay? When you take your test, you're going to have 2 attempts on it, all right, which I think is fair. So you can have 1 chance to go through it. Once you see the questions, you can go back and watch this video again and then take it again. And honestly, if you take notes during this review, use them during your test, I think you're going to do just fine. Okay? All right, so what do you need to know? Number 1, electromagnetic waves. Okay, so write this down. Electromagnetic waves, okay, are vibrations. Okay? They're also known as light, and if you remember, the most important thing about them is that they do not need a medium to travel through, okay? A medium is something that a wave can travel through, and mechanical waves need a medium, all right? This is from last 6 weeks. So think about like a water wave, okay? A water wave is simply energy, right? Something is pushing the water, all right, and that causes the wave to form. There's some sort of kinetic energy that's going into the water to create that movement, all right? If there was no water, there would be no wave. Same thing with a guitar string. If there was no string, okay, there would be no wave going through the guitar string. And this means that mechanical waves move the fastest through dense mediums, right? So remember, when we talked about sound is a mechanical wave. If there is no air or water or solid for the sound to move through, there is no sound. Remember, in space, no one can hear you scream. So with sound traveled the fastest in hot substances because the atoms are vibrating quickly, and it traveled the fastest in dense substances because those atoms were close together. So, right, so sound travels slow in the air, it travels really fast through solids, and it doesn't exist in the vacuum of space because there's no atoms. Electromagnetic waves travel the fastest through a vacuum because there's nothing in their way. That's how I like to think about it. Electromagnetic waves are their own vibrations, and they don't want any atoms in front of them, okay? That's why that's why electromagnetic waves travel fastest in space, second fastest in the air, and they travel slower in water and slower in solids. That's number 1. Number 2, you gotta remember the spectrum itself, okay? So, you may remember we came up with a little acronym here. I'm gonna write this down, okay? It was Raging Martians invaded Venus using X-ray guns. All right, I'm gonna hold that up here, okay? Radio, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays, okay? This is the electromagnetic spectrum. And what you need to remember, okay, visible light right here, this is what we can see, okay? You need to remember your colors, and in order to do that, you got to remember a gentleman's name, which you do. His name is Roy G. Biv. All right? Now, Mr. Roy tells us that we go red, orange, yellow, green, blue, indigo, violet. All right? The reason that this is important is because all of these are light waves. All of them are electromagnetic waves. The only difference between them is their wavelength, okay? And if you remember, the wavelengths look like this. The wavelengths are long on this side, and as they go over here, they get Shorter and shorter and shorter. This is a terrible drawing, obviously, but, okay, what you need to know is that radio waves over here have long wavelengths, and gamma rays over here have really short wavelengths. What does that mean about the frequency? You know what that means. If you have a long wavelength, that means you have a low frequency. Radio waves, low frequency. Microwaves, a little bit higher. Infrared waves, a little bit higher. But these three are not harmful because their frequency is low, because their wavelengths are long. Visible light, okay, is also harmless. Visible light doesn't hurt anybody. I mean, unless you shine it in somebody's eyeballs and burn out their optic nerve. But we're not talking about that, okay? In general, okay, this is not dangerous, okay? All of these are a form of light, which means they're a form of radiation. But they're not dangerous radiations until we get to ultraviolet, okay? This side of visible light, not dangerous. This side of visible light is dangerous because it has a high frequency. These have short wavelengths and big frequencies. Ultraviolet light causes sunburns. X-rays can cause cancer, okay, which so can ultraviolet waves. They can cause skin cancer. And gamma radiation has the shortest wavelength, which means it has the highest frequency, which is why it's the most dangerous. Okay, we see this coming out of nuclear explosions. All right. Radio waves and we use for communication. Microwaves we use for cooking things. We also use them for communication. And as you remember, infrared waves we use in night vision goggles. Wink. Okay. Here are your colors. Again, red has a long wavelength and violet has a very short wavelength, in which case it's the only difference between these colors is their wavelength. Red has a low frequency, violet has a high frequency. Okay? All right. Up next, wave behaviors. Okay? All right, so we remember all of the wave behaviors. The first one we'll talk about is reflection. Okay, so if you have a surface and a wave, let's say you have somebody looking in a mirror, it's a terrible smiley face, okay? What's gonna happen is light's gonna bounce off of that person and in to your eyeball, which looks like that, all right? That's why you can see things in mirrors. When you see this, you do not see a real image, you see a virtual image, which is gonna be right there, right? When you see a mirror, it looks like there's somebody on the other side of the mirror, equidistant away from you, right? If you're looking at the mirror and you're standing 3 feet away from the mirror, you think you're looking at you 3 feet on the other side of that mirror. You're not. It's not a real image. Remember, real images need to be projected using a projector, okay? Virtual images are just optical illusions, all right? Next. Oh, also, remember the law of reflection. Whenever you have a light wave bouncing off of a surface, you draw a normal line coming off of that surface, and this angle here, the angle of reflection, equals this angle. Oh, excuse me, I got those backwards. This is the angle of incidence, and that equals the angle of reflection. Again, terrible drawing, but you get the point. All right, up next, refraction. Refraction is what happens when a wave changes mediums. It changes what it's traveling through. So it either goes from air into liquid, liquid into air, solid into liquid, whatever that is. 9 times out of 10, 99 times out of 100 on a physics test, it's going to be going either from air to water or water to air. We saw this with your Jello lab, okay? So in this case, here's your surface. Let's say this is the air and this is the water, okay? All right, if you have light going like this, so you have a light wave, okay, that's traveling, and it hits the water. Well, what's it gonna do? Well, what did we say? Where does light move the fastest? Light moves the fastest where there are the least amount of atoms, okay? Well, where are there more atoms? Are there more atoms in the air or the water? Which one's denser? okay? Well, if you've ever tried running in water, you know water is much denser than air, right? There's more atoms in the water, okay? There's more atoms in the water, which means the light is going to slow down as it goes into the water. So what does that mean? Well, it means we're going to draw another normal line, okay? That dotted line is imaginary. It's 90 degrees to the surface, all right? And depending if the light speeds up or slows down, it's either going to go towards the normal line or away from the normal line. So how do we remember this? If the light speeds up, it goes away from the normal line. I remember, speeds up, runs away. Again, write this down. Slow down the video. This is very helpful, I promise. If the light slows down, it goes towards the normal line. So in this case, we're going from air to water, which means that it's going to do what? Well, in the air, it's moving faster. In the water, it's moving slower, so it's going to slow down. That means it's going to bend towards the normal line, okay? This is the direction it wants to go, okay? It's going to go towards the normal line. If it's sped up, it would go away from the normal line. So in this case, it's going to go like that. It wanted to move this way, but it didn't because it slows down. That's why the pencil looks bent inside of a glass of water. Okay. We also saw diffraction. Diffraction is what happens when a wave goes through a small opening or it hits an object, is really what it is. And if you remember, there's your opening. Okay, the waves go straight. Think of water waves moving straight, and right? And then they hit the opening. What do? You know this. They bend like this. Okay. Imagine a big flood of water hits a door. When it goes out of the door, it's not going to keep going straight. It's going to spread out. This is called diffraction. All right. Up next, we have polarization. Okay, this is too difficult for me to draw, but what you got to remember is that in polarization, okay, light is a special kind of wave. And again, this is radio waves, microwaves, visible light, ultraviolet, all of it. All radiation, okay, vibrates in multiple different ways. It's vibrating up and down, side to side, diagonally, okay, all the time, all right? If you polarize light, what you do is you put it through a filter, okay? So imagine like a gate, okay? When we polarize light, what you're doing is you're putting a gate. It's either a vertical gate or a horizontal gate. If you use a vertical gate, okay, those horizontal and diagonal waves, when they hit it, they stop. They can't go through because they're vibrating the wrong way. Only the vertical waves come through the gate, all right? Similarly, if you have a horizontal filter or a horizontal polarizer, okay, when vertical waves hit it, they can't go through. Only horizontal waves go through it. We use vertical filters to block horizontal waves in polarized sunglasses. Horizontal vibrations are the ones that cause glare, and if you remember from class, that's why you should spend an extra $15 on vacation and buy the polarized lenses. The last one is total internal reflection. You may remember the video from class, and again, if you don't remember the video from class, go back. I posted the PowerPoint. All of these are under light wave behavior. They're all in there, okay? Total internal reflection just tells us that if you have a prism, okay, when light hits this prism, it's going to reflect out, okay? And as you increase this angle, eventually you're going to hit an angle where that light doesn't refract anymore, it doesn't bend, it starts to reflect, okay? We watched a video about this in class. That video is posted on the PowerPoint under light wave behavior. What you got to remember about total internal reflection is that because of this, we have fiber optic cables, okay? And that's how we use it. It's the most known use. It's also the reason why you have those little flexible plastic flashlight toys that you see at the fair. That's also total internal reflection. Okay, optics, okay? If you guys remember, in class, we saw a lens. Okay. Oh, let's talk about lenses first. There are two types of lenses. Okay. Same with me. We have concave lenses, okay, and convex lenses. Oh, excuse me, I got those backwards. We have convex lenses. Excuse me, I'm going to write that down so I don't get it wrong again. And concave lenses. We know this is concave. I just corrected myself because the sides cave in, right? Okay, what do these do? When light waves hit a convex lens, they converge. And it's our SAT word for the day, right? If the light waves converge, that means they come together. Okay, you've seen this before. If you've ever played with a magnifying glass, that is a concave lens. It brings the light waves together. So if you ever tried to burn grass with a magnifying glass, that's a concave, excuse me, why do I keep saying that? It's a convex lens. Say it one more time, sorry. It's a convex lens. Convex lenses converge. Concave lenses diverge the light, which means when light hits one of these, it spreads it out, okay? If you are nearsighted, such as myself, okay, if you can't see far away, look at your glasses, and you'll notice that the edges of your glasses are thick on the outside and thin in the middle. That's because you probably are wearing concave lenses on your face. All right? Next, optics. What you need to know. This is a convex lens, okay? As we saw in class, we can use convex lenses to make images. That's because they bring the light together. They can focus light and we can make an image. All right, so on one side, we have an object. All right, like for example, the candle. Remember, I had the ruler, it had a candle on one end, it had the lens, the convex lens in the middle, and there was a piece of paper. Well, that piece of paper makes an image. Okay? Remember, the image is always going to be inverted, which just means that it's upside down, right? Okay, so what you need to remember is what happens when you move the object closer to and farther away from the lens. What you got to remember is that the image and the object, they're stuck together, okay? If you move the object to the right, the image moves to the right. If you move the object to the left, the image moves to the left. It's like they're stuck together. So if I move the object towards the lens, the image moves away from the lens. If I move the object away from the lens, the image moves, that's right, towards the lens, okay? And the only special things you got to remember are those F's, okay, and two F's, okay? So what you got to remember here is that if you move the object to F, if the object is right here, there's no image, okay? If you put the object on the focal point, those waves don't converge at all. They become parallel. There's no image. If you move the object in front of F, okay, what you're going to get here is a virtual image, meaning that there's absolutely no image, okay? So the object has to be behind the focal point. I'll say that one more time. The object has to be behind the focal point, okay? In this case, if you have the object way out here, okay, beyond 2F, that means that your image is going to be somewhere between F and 2F. That's important. Okay, almost done. The only other things that you got to remember for the test are what we talked about with electricity. I've been covering this on all my other videos, but just real fast, you got to remember that in an atom, okay, in the center of the atom, you have, okay, in the center of an atom, you have what's called the nucleus that has protons, neutrons, Man, this is really bad. And electrons. That is arguably the worst words that I've ever written in my entire life. And I'm including when I first was learning how to spell in kindergarten. This is the worst. Okay. Protons and neutrons make up the nucleus of the atom. It's the biggest part of the atom. It's the center of the atom. And for right now, we don't mess with the nucleus. If you mess with the nucleus of an atom, you get a nuclear reaction, which is a massive amount of energy. We will talk about them in the upcoming weeks, but for right now, protons and neutrons do not move. If you add protons to an atom, you change the atom. One proton is hydrogen, two protons, okay, now you have helium. It's a completely different element. If you add a third proton, you get lithium, which is a metal, that's a rock, okay? The electrons are really small. They're negatively charged and they're outside of the atom. These move easily from one atom to another, okay? When electrons move, they create electricity. That's why they're called electrons, all right? Okay, some objects really like for their electrons to move. Their electrons can move very easily. If electrons can move easily from one atom of a substance to another atom of the substance, that substance is called a conductor because it conducts electricity, all right? If a substance does not let its atoms lose and gain electrons, if a substance likes to keep its electrons, okay, right here, and those electrons can't move, that substance is called an insulator, okay? And you know this. Conductors are metals. Things made of metal really like to let their electrons move around. Things such as wood and glass and, I don't know, your hair. Well, actually, here's a bad example. But like wood and glass, rubber, plastic, all of those things, those are all insulators, okay? And the last thing you got to know is what we've been talking about for the last couple of weeks, and that's just Ohm's law. Ohm's law tells me I equals V divided by R. I is current. Okay, I is current. Current is how fast the electrons are moving in a circuit. We measure it using amps, or A. V, you got this one, is voltage. Okay, voltage is how many electrons are moving. We measure that in volts. And last but not least, we have R, which is resistance, and it is measured in these horseshoe-looking things, which are called ohms. All right? This is your equation. We've worked through this a million times. If you don't remember how to use it, again, go back and watch one of my earlier videos on series and parallel circuits. But if you're given the voltage, the current, and the resistance, you just use this to solve it. Okay? And you always do the opposite. So I guess I'll do an example real fast. Let's say I know my current is 5 amps. Let's say I know my resistance is 3 ohms, and I'm looking for the voltage. Again, number one, always make a chart, okay? Here is what I know. I know my amps, I know my ohms, I'm looking for my volts. Write down your equation. I equals V divided by R. Plug in your numbers. Okay? My I is 5, boom. My R is 3. Oh, I didn't plug that in. There you go. And my V is I don't know. You got to get the V by itself. So we see what this is. This is division. You do the opposite of whatever you see. So you multiply both sides by 3. 3 divided by 3 cancels out. And 5 times 3 gives us a voltage equal to 15 volts. All right? Okay. Last but not least, you need to know about series and parallel circuits. And I just did a whole review on this. So watch that video. Again, you're going to have a couple days to finish this test. So take your time. All right? We'll talk about that in a second. What you got to remember, series circuits, parallel circuits. Okay? In a series circuit, it's one loop, which means you got a battery in one loop. In a parallel circuit, you have multiple loops. So like here would be a resistor, here would be a resistor, and here. Okay, your resistors are in separate loops from each other. Okay, and what you got to remember here is that in a series circuit, okay, in a series circuit, the voltage drops, the current is the same, and the resistance adds up. What that means is everywhere in a series circuit, the current is the same everywhere. I remember this because I's look like 1, all right? And that means that there's only one loop. So I remember that a series circuit, the current is the same everywhere. Write that down, all right? In a parallel circuit, okay, the voltage drops. Oh, excuse me. The voltage is the same. The current drops. And the resistance is weird. Okay? Here, the voltage is the same everywhere because they're all connected to the battery like they're their own loop. They're all in their own loop, so they all get the same amount of electrons. But the current is different, okay? And when I say it drops, what that means is that let's say there's 5 amps of current. Well, maybe this one gets 3 of those amps and this one gets 2 of those amps. It splits up. Similarly, over here, the voltage drops, which means if this is like, let's say this is a 9-volt battery, let's say this one gets 3 ohms, this gets 3 volts, this gets 3 volts, and this gets 3 volts. Okay, they all get a piece of that big pie. Okay. Again, watch my video from yesterday. It has everything you need. I go through 4 examples of series and parallel circuits. Just remember to use the VIR chart. Voltage equals current times resistance. It's Ohm's law, just in a different way. Write down your number of resistors, write down your total, and then figure out if you're using a series circuit or a parallel circuit. If it's a series circuit, all of your currents are going to be the same, right? Series is 1, there's 1 loop. If it's a parallel circuit, all of your voltages are going to be the same because parallel circuits split multiple loops. So the voltage is the same everywhere. Okay? I am going to put this test up. You will have 3 days to complete it. I'll put all of the guidelines in my post on Google Classroom. You will have 2 chances to take the test. So what I want you to do is to watch this video, write down a big page of notes. If you use this video and the notes that I just gave you right now, you'll ace the test. I promise, okay? Take it, see how you did. Go back, watch the video again, check your notes, and then take it again, all right? If you have any questions, email me. Also, your superpowers. There's some really interesting superpowers out there. I really enjoyed a few of them, and I should have them. The ones that I like. I got a lot of normal ones: flying, reading people's minds, teleportation, super strength, super speed. I liked a lot of that. There's a lot of super speed. Are you guys watching The Flash? That's what I think that's coming from. Somebody said that they could, that they wanted to be able to fill anything up. I thought that was interesting. I don't know if you're talking about like somebody's water cup and you want to be polite, or if you want to be able to like fill up somebody's pool. I thought that that was a really interesting one. Somebody said that they wanted to be able to speed, visible, time travel. That was a really good one. A lot of people want to be Superman. But yeah, anyways, that was really good. Those really struck me. Anyways, hope you have a great day. Email me with questions, and yeah, be good.